Welcome to Engineering Studio with Dr. Mohammad Tahir. In this video, we are going to discuss about the design flowchart for build-up members and design of lacings. So first of all, design of built-up sections. So built-up section, when they are under compression, so their design will be exactly similar as that we have studied previously for the compression members. So first we need these information. The applied load, we need the factored applied loads, we need unsupported length in XY direction, and we need the effective length factor Kx and Ky. Then we need to assume the slenderness ratio to initially calculate the required area, because at that stage we don't have the section properties or section dimensions. So first we will assume the value of R, then based on that assumed value of R, we can calculate phi CFCR. So after calculating phi CFCR, we can calculate the required area, which is equal to PU divided by phi CFCR. After calculating the required area, we need to select the section based on area required and B greater than B minimum. So we need to select the built up section, and we need to select such a section that it has almost equal slenderness ratio about both the axes if we don't have intermediate bracings. After selecting the section, built up section, we need to perform the local stability check, mean we need to check for lambda equal to B over P or H over TW, and it should be less than lambda R. So after checking the local instability, we need to check for the global instability. For that, we need to calculate the slenderness ratio. The slenderness ratio in X as well as in Y direction, or we need to select the critical slenderness ratio, the largest out of X and Y slenderness ratio. So if it is less than 200, then it is okay, otherwise we need to revise the section. If it is less than 200, so it means our section is globally stable. So after that, we need to calculate phi CFCR based on the slenderness ratio, critical slenderness ratio value, or the governing slenderness ratio value. So after calculating the phi CFCR, we need to calculate the capacity of section phi CPN, which is equal to phi CFCR multiplied by area of selected section. If it is greater than PU, then it's okay, otherwise we need to revise the section. So this procedure is same as we have done earlier, we have discussed in the previous videos. We have solved few examples, we have discussed the flowchart for the built up members. So here one thing that need to be noted, that in case of built up section, when we use lacing to connect the elements of the built up section or the individual members of the built up section, so if we use lacing, so in that case the distance between the lacing point will be sufficiently less. But if we use tie plates, so one type we can only use 2 or 3 tie plates. So in that case, the distance between the tie plates will be sufficiently large. So in that case, in the case of tie plates, the slenderness ratio of the individual member between the tie plates A over Ri can be sufficiently large, and the member can be buckled at the local position or between the tie plates. But in case of lacing, the distance between the unsupported length of the individual element is less, and the slenderness ratio of the section in between the lacing point will be low, so A over R will be sufficiently less. So it means there will be no chance of buckling in between these lacing points. So for that, if this A over R is very low, so in that case the modified slenderness ratio will also be very small, because modified slenderness ratio is KL over R naught square plus A over R square. So when A over R square is very small, so it means the modified slenderness ratio will be close to this value. So in case of lacings, we don't need to check for the modified slenderness ratio, we can skip that. We only consider Rx and Ry, and we can select the larger value out of these two as a governing value. Okay, after that, next is once we have finalized the section, built up section, the next is design of lacing. In the design of lacing, we assume that the lacing element should resist the shear force which should be equal to 2% of the axial capacity of the member phi c Pn. So the lacing element should be capable to resist the shear force equal to 2% of the axial capacity of the section. Okay, based on the shear force, we can calculate the force in the lacing element, compression or tension. So most of the time the critical value is compressive force. So the compressive force in the lacing element Fu can be calculated by using this expression Vu over n sine of theta. Here Vu is the shear force that this lacing element should resist. N is the number of faces. For example, we have built up channel section, so one face and the other face. So this is N, and this is for single lacing, and if we have double lacing then we need to divide it by 2. So we have already discussed about this expression in the previous video. Okay, after calculating the Fu, the next step is to calculate the length of lacing bar. So length of lacing bar is equal to S over sine of theta. So this is S from here up to here, and this length will be equal to, if this angle is theta, so this will be LE will be equal to S over sine of theta, or we can say LE sine of theta is equal to S, so we can write LE is equal to S over sine of theta. So this is for single lacing, but if we are using double lacing, so in that case we need to multiply it with the factor 0.7 for double lacing. Okay, after calculating the length of the lacing, the next step is to check the slenderness ratio of the flange of the section in between the lacing point. So for that we have this expression 4.61 L over TF, mean length between the distance between the lacing points, and TF is the thickness of the flange, and it should be less than R, the governing value of the overall section. The governing value of slenderness ratio for the overall section, larger of Rx or Ry. And here the factor L, this should be equal to L S cot of theta or 2S cot of theta. For example, if we are using this single lacing, this distance this is S and this is LE, and this much distance, for example if I say it is X, so it is equal to actually S cot of theta. And if the lacing is like this, so the L will be equal to 2 times this X, so we can say LE or L is equal to 2 times S cot of theta. So from here we can determine this distance between the lacing points. Once we have distance between the lacing point, we need to check this expression. We need to satisfy this expression. If this is satisfied, then okay, otherwise we need to increase this angle theta so that the distance between the lacing point can be reduced. When this distance is reduced, so it meant this factor is reduced, and we can satisfy this expression. Okay, after satisfying this expression, the next is we need to check for the slenderness ratio of the lacing element. So the slenderness ratio of the lacing element mean LE and R, radius of gyration of the section. For example, if it is a rectangular section, so it is B and T, so R will be equal to I over A square root, and I is equal to BT cube over 12, and A is equal to B into T. So by using this expression we can calculate R. So the slenderness ratio of the lacing element should be less than 140 for single lacing and less than 200 for double lacing. Okay, after that, based on the slenderness ratio of the lacing, we need to calculate phi CFCR value just like a compression member, and then based on this phi CFCR value we can calculate area required for the lacing element. Once we have area required for the lacing element, then we need to decide what will be the B and what will be the T. We also need to satisfy the local instability check B over T, and it should be less than 10.8. We also need to satisfy this expression that B minimum should be more than 3D. So if we are using a rectangular bar, so in that case this B should be more than 3 times diameter of rivet. So determine the section for lacing bar satisfying the above requirements. So we need to satisfy these 3 requirements. Mean it should satisfy the slenderness ratio for the global instability. It should have the area more than the required area. It should also satisfy the local instability check, and the B should be more than B minimum. So based on that we can decide the section for the lacing element. And then at the end we need to design for the tie plates, and for the tie plates the thickness of tie plate should be S/50 and the length of tie plate should be equal to S.